Good morning, everybody. I will wait a couple more minutes. We'll get started right at 10. All right, I think I'm all set up here. Is this working? Yes. Okay. All right, good morning, Daisy. So as we said last time, we're going to start with kind of reviewing the naming using this worksheet from last week, this practice sheet. Hopefully you had a chance to try some of this. Good morning, Monica. And then from there, we'll go into the new stuff, which is the Lewis structures or drawing chemical structures. Hey, Lene. Hey, Alyssa. Welcome. All right, we got some folks here. So thank you for joining me this morning, everybody. So hopefully the naming thing is going okay. I know some of you are having some issues with it. It is a tough thing. It's probably the most work that we've done so far, the most difficult thing. So it is going to take some work. You can ask me for more help. We can do some other live sessions other times, like on like where we can see each other and I can help you, kind of like an office hours kind of thing. There's also tutoring through the tutoring center at Harper College if you're interested in that. So let's take a look at some of these. If you've got your own sheet, go ahead and bring it out. I'm not going to go through every single answer because the answers are posted on Blackboard, but I'll just pick a few. If there are particular ones that you weren't sure about or that you didn't understand where that answer came from, if you could post it either in the chat or the live streams Discord, and then I can make sure to do those. So first question, if we have a semi-metal and a non-metal, is that covalent like problem 5? Yes. So good question. So if you look kind of behind me here, on the green ones, the semi-metals that kind of go through this way, we're going to consider all those to be ionic So you got boron, silicon, germanium, arsenic, antimony, and tellurium. Those are all going to be considered covalent. And then the orange here that are right next to them, those we're going to consider as metals. So aluminum, gallium, indium, tin, and so on. For the purposes of our naming system, we're going to consider those as metals. So let's do this one. So this one we consider covalent, which means that its name is silicon dioxide. All right. Hello. Okay, let me take a look at the, I'm just going to jump around to a few different ones here. I want to look at COBr2. So first we categorize that, ionic covalent. It's a metal, non-metal, so that makes it ionic. And then the other type of classification we want is that it has a variable charge. And I know that the answers here are actually from a different faculty member who designed this sheet, so they may use a little bit different language there. As far as classifying the type of compound, I don't care about that so much. That's a means to an end. The point of the classification is so you can get the name right. So however you want to name or think about those names is fine. But the important thing is that we know how to use the rules once we get there. So this is going to be cobalt and bromide, but because cobalt is the variable charge metal, we know we need parentheses there. So we would say, all right, cobalt, what charge? It goes in the parentheses. To figure out the charge, we look at bromide, which we know is -1. And so if we have 2 -1 bromides, then cobalt has to be +2 to balance that. So a 2 goes here. Okay. Binary is correct. Yeah. Binary just means there's only 2 elements. There's a metal and a non-metal. So Monica says that Daisy sent a chat on Discord. I don't see it. Where? Morning, Maria. I don't see that. Let me know if you can find it and or where I should look for it. Okay, let's take a look down at this one. FePO4. So here we have again ionic metal, right? So this is ionic. And this one is not binary. This one is not a binary ion or a binary ionic compound because there's more than just 2 elements here. So that tells us that the nonmetals are part of one of the polyatomic ions. Oh, I see. Okay, that makes sense. Thank you. I thought you were trying to tell me something. No, that's fine. All right, so ionic and polyatomic, and this is also going to be one of the variable charge ionic. So because iron can have more than one charge. So just like above the one we just did with cobalt, we're going to have iron and we're going to have phosphate. Remember, you can't get that name from the periodic table. You have to get that name from the list of ions. You don't have to. I don't really care how you categorize it. I really don't care about the left column. I'm never going to ask you on an exam what type of a compound is this, other than maybe ionic or covalent. Because those other words they're arbitrary. Like you could pick, different books are going to pick different words to describe what that means. The important thing is that you know which rules to use. So you have to know that iron is a variable charge. You have to know that iron can be multiple different possible charges so that you know that you have to put the parentheses. Because if we don't know that, if we don't know that it needs the parentheses, then it is going to be wrong. So however you want to name that to tell yourself that you need the parentheses, that's what's important. So iron, here we have to figure out the charge. And in order to do that, we need to know the charge on phosphate. And that's something we can't get from the periodic table. That's something we get from our list of memorized or not memorized probably at this point, polyatomic ions. So we look that up and we find that phosphate is -3. And so if we have a phosphate that's -3, that means that our iron must be +3 to balance that out. So -3 +3, and so we're going to put a 3 here. Okay, binary, polyatomic, ionic, and covalent. Yeah, those are all fine labels as long as you remember that some ionic compounds need the Roman numerals in parentheses and some don't, and you understand the difference between those. But yeah, you've got the important distinctions. That's right. Okay, so let's see. Monica sent in the Discord a table to figure this out. Yeah, that's correct. Yep. Yep. So if that's helpful for you, I'll take a look at that. It's in the general channel. Okay, number 12. Yeah. So again, we have to figure out this charge, we need to look at what's involved in the compound. So we looked at this last time. So the formula here, Ti, and then in parentheses SO4 tells us that we have one Ti, and actually let me get rid of the charges so we can figure that out again this time. So this formula here, Ti SO4 tells us one Ti and two SO4s. That's what the formula tells us. But the number in the parentheses is the charge on titanium. So to figure out that charge, we need to know what are the charges of the anions, the sulfates, and then what does titanium have to be so that the overall charge becomes neutral. So sulfate is -2. And so if there are two of them, that means that our total negative charge in this compound is -4. -2 and -2 is -4. So therefore, the titanium has to actually be +4 to offset them, right? Because you need an overall neutral compound. So if you have 4- overall, you need 4+ to balance that out. And so that's why the titanium gets the 4 rather than the 2. And that's another reason why the idea of like crisscrossing the charges can be helpful, but you also have to actually know where that comes from. Because in this case, if you just like reverse flip-flop the charges, you're going to get it wrong because titanium is not 2+, it's 4+ here because sulfate is -2. All right, let's move on to the names. So going from the names to the compounds, generally with these, the easiest ones are the covalent ones. So something like dinitrogen trioxide, as long as you know what those prefixes mean, you can get that formula because that's just directly the number of each type of atom. Where it gets a little bit trickier is in the ionic compounds. So copper 1 chloride. Let's think about what information do we get from the names, and then how do we put that together? So just to give myself a little more room, I'm going to zoom in on this a little bit. So copper 1 chloride, you want to first ask yourself, what does that tell us? All right, what that tells us is what are the two ions? So we can look up that copper is Cu and chloride is Cl. And then what are the charges of those ions? Chloride we get from the periodic table is -1 because all of the ions in that column are always -1. And copper, the charge is given directly by the number in parentheses. So that's +1. So we've got copper +1 and chloride -1. Now we can put them together in a ratio that allows for them to be neutral overall. So to do that, we look at our total positives and our negatives and figure out how we need to adjust those. Well, here it's pretty simple. +1, -1. So we know that our formula can be CuCl. And of course, this is ionic. This has the same kind of classifications as above. But notice that when we're going from the name back to the compound, it's less important to categorize it because the categorization really just helps us figure out which type of naming rules we need. If we already have the name, it doesn't really matter so much which type of rules because we can see what the name looks like. Okay, let's look at the next one, lithium acetate. So acetate is a polyatomic ion. You won't find it on the periodic table. One clue from that is that it ends in -ate instead of -ide. So that tells us it's got to be polyatomic. And we can write that down like this. Remember that we need the formula and the charge from the chart or from memory. That we can't just figure out the charge once we have the formula. So then for lithium, we can look that up on the periodic table as Li. This one, the charge is not given in parentheses, and that tells us that the charge is always the same. So then when we look at the periodic table, we can see that it's in column 1A, and therefore the charge is +1. So once again, we have +1, -1, so we can just stick those together. Okay. Any of these other ones that gave you particular trouble or that you want to check? I want to look at one more. Go ahead and post whatever other ones you want to look at, but I want to look at ammonium oxide. The tricky thing about this one is it's ionic, but it doesn't actually have any metals in it. Ammonium is not a metal. It's not on the periodic table. It is a polyatomic ion. So it is NH4 plus, and oxide is O2 minus. So here's an unusual compound for us in that it's ionic, but it does not contain metals because the cation is a polyatomic cation, ammonium. So we still do everything the same as other ionic compounds. We just think of this whole thing as the cation, NH4 plus. So we say, okay, we have a +1 and we have a -2. So that means we need 2 of the +1s to balance out the -2. So the way we write that compound is NH4 2O, like that. Okay, so hopefully this is going okay for you. Again, if you have issues, if you find particular ones that didn't match up with the solutions or you're not sure where they came from, please ask. And there's lots of other practice. Of course, you're probably done with the Master in Chemistry by now, but if you look through on the internet, there's lots and lots of naming practice. And come see me if you're still having trouble with this. I mean, I guess come see me, not in person, but like send me messages and we'll find a time to meet up and figure it out. All right. So let's take a look at our next topic, which is Lewis structures or Lewis dot structures. So last, actually, I don't remember if it was, I don't think it was last time. I think it was 2 times ago when we did those buckets of electrons where we looked at how many electrons are in each of these shells. And then we said the outermost one was called the valence electrons or the valence shells. So you can do that. And here's a diagram of those first 3 rows of elements with their valence electrons, those outermost electrons. So these would be the electrons in that outermost bucket when we fill those 2, 8, and 8 buckets. And it turns out that that number is actually really important because those are the electrons that actually do the chemistry, that do the bonding, that do the stuff. So we want to know always how many valence electrons, those outermost electrons, does an atom have. And luckily, for most of the ions we care about, it's actually pretty simple because the periodic table is organized by valence electrons because it controls the chemical properties. So you'll notice like everything in column 1 here has 1 valence electron. Column 2 has 2. And then we jump over this. These are kind of smashed together to save space, but we jump over to the boron. And then we've got boron and aluminum with 3, 4, 5, 6, 7, and 8. Hey, good morning, Patty. I think you're in the wrong class, though, right? I mean, you're welcome to join. If we look back at the periodic table, you can see that organization here, and actually you get a hint by the top of the columns. So helium actually has 2, so that's wrong. That was my mistake, because there's only 2. Remember, there's only 2 electrons that fit in that first shell. So you can only have a maximum of 2 for helium, and then or 2 valence electrons for helium from that first bucket, and then we can go on from there. So if we look up, you can actually see those column numbers on the top, and those correspond to the number of valence electrons for those columns. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, with the exception of helium. So we can use the periodic table to figure out how many valence electrons there are. Now, a Lewis dot structure is simply the atom with little dots showing their electrons. So that's what the Lewis dot structure represents. They represent the electrons. And then they get distributed in this particular way so that it's really easy to quickly visually check how many electrons they have and how many kind of spaces they have, or how many areas that they could be paired up. So a full valence shell would be 8 electrons for everything except helium. And so we can see, like, oh, fluorine here, it's clearly missing 1. We have 7 valence electrons. It really kind of wants 1 more. Oxygen, we can see it's like missing 2 pairs. Nitrogen, it's missing 3 pairs. So the earliest way of building compounds, what we called covalent compounds, and the reason they're called covalent is because the original idea was, well, you could take 2 atoms like this, chlorine and fluorine, and if they got close enough together, then those electrons could actually be in both valences at the same time. So that would make them both have 8 instead of just 7 and 7. So that full valence shell is particularly stable. Elements, we can say, I mean, they don't have desires, but we can say that they want to have full valence shells. So if they only have 7, we got 7 and 7. Let me use a couple of different colors here to demonstrate this. So this one's got 7, and this one's got 7 when they're apart. But when they get close enough together, those electrons actually penetrate each other's valence shells, and so they count for both. So we actually count those shared electrons for fluorine and say that it has 8. And then we also count those electrons for chlorine and say that it has 8. So we would say that when they are connected like this, they each have 8 valence electrons instead of 7. So they each have a full shell. And the word we use for that is the octet rule. That's that idea that they want to have 8 electrons. And again, hydrogen and helium are exceptions to that. There's a couple other exceptions too. I'm not sure we'll get into that here. So if one has 8 and another has 6, does it work? No. So the noble gases, the ones that already have 8, like here, neon and argon, really don't make compounds. They don't covalently bond. There's some exceptions farther down the table for some other weird reasons, but they basically just stay by themselves. So they don't have any incentive, we can say, to connect. So when we build these compounds, our goal is always going to be to make sure that all the atoms have full octets, is the way we're going to say it, full octets. And that means 8 electrons in each. So those 2 shared electrons are kind of special because they're shared, and so they're called covalent. They're in both valences at the same time. And usually, instead of drawing them as 2 dots like you see here, we draw them as a line. But that line actually means the same thing. So line doesn't just mean 2 things next to each other or connected. It doesn't mean ionic. We don't use lines for ionic compounds. It specifically means 2 shared electrons. Right? So that line means 2 shared electrons. So then when we do our accounting, when we figure out if the atoms have, how many electrons the atoms have inside the compound, we would say chlorine here in this compound has 2, 4, 6, 8 electrons. We count both of those covalent electrons. And then fluorine also has 2, 4, 6, 8 electrons. So we would say they both have full octets here. Other electrons that sort of just come along with the atom are not involved in bonding, and those are called lone pairs of electrons. Sometimes they're called non-bonding electrons. Those are just electrons that are kind of hanging out on that atom and not participating in the connection. All right. So what we can do then, and we will kind of build up to this and try to figure out some of these, how to build bigger and bigger structures just knowing this information. So let's start over on the left. So we can draw a Lewis dot structure of oxygen, and that is simply just oxygen with dots representing the valence electrons. So oxygen has 6 valence electrons, which we can get from the periodic table. So let's review how we get that. We find oxygen right above my head here. That's in column 6A, 6 valence electrons. If you want to derive it elsewhere, or you don't, all you know is that oxygen has 8 total electrons, then you use the bucket method that we talked about before, and you still find 6 valence electrons. All right, so then we draw those 6 valence electrons on the atom. 1, 2, 3, 4, 5, 6. Let me redo that actually. The best way to do this, because remember, we want to know which electrons are paired and which are not. So really the right way to do that is to go put 1 electron on each side first, and then start pairing them up until you run out of electrons. So there's our 6 electrons. All right, now how does that change if instead we want to draw a Lewis dot structure of oxide? So what do you think that 2 minus means? How does that change our dot structure? Any ideas? What do we do with the dots if we've got 2 minus? So it's a good guess. We put 4 only. What does it mean for an ion to be minus 2? So are electrons positive or negative? They're negative, right? So if we take away 2 electrons, yeah, so if we had 2 more protons than electrons, what's the charge on the proton? Protons are positive. Electrons are negative. So if we had 2 fewer electrons, would that make it more negative or would that make it more positive? If we had fewer electrons, it makes it more negative? Yeah, more electrons. So we just got that backwards. If we want to get more negative, we need more electrons. If we want to get more positive, we need more protons, but we can't add protons. So to make it more positive, we take away electrons. So in this case, it's 2 minus, so that means 2 more electrons. So we go 1, instead of 6 electrons, we have 6 valence electrons, we now have 8. So we go 1, 2, 3, 4, 5, 6, 7, 8. And then to indicate that that's actually minus, we want to put a charge on there. So this is just 1 atom. But normally, like if we had a big compound and we still had a charge, we would make some brackets so we could see that the charge is on that whole thing, and then put the charge up there. Now notice that that we now have actually a full octet. This oxide ion has 8 electrons. And in the last unit, we were talking about how oxide is particularly stable. It's the most stable ion of oxygen. It's what the ion that oxygen most often makes. So now you can kind of see why that is, because the minus 2 ion of oxygen is particularly stable because all of the electrons are paired up in the valence shell. Okay, so now let's try to build our first compound. We're going to build O2, dioxygen, which is the standard way that oxygen exists in the world, elemental oxygen. So here's what we do. We have 2 atoms to deal with, and there's a couple ways to do it. First, we can look at the dot method, and then we'll start building out into our structure method. So for the dot method, what we would do is we would take the 2 oxygen atoms that are listed in the formula, and we'd write down their Lewis dot structures. So it doesn't matter where you put these dots, but we want to show that there are 2 unpaired. So there's our 2 dots, and then we think about, all right, how can we share these electrons? So how can we make covalent interactions so that the oxygens have the correct number of valence electrons, which is 8. So instead of 6, they have 8. Now we can't just transfer them over because then one of them wouldn't have enough. We want both of them to have 8 electrons. So the way we do that is by sharing pairs of electrons. So let's say we want to share those. that would lead to something like this. So we've shared those two, and then we still have to account for everything else. So you'll notice that doesn't quite solve our problem. If we count the number of electrons on each oxygen atom, there we get 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that's not quite right, because we know that oxygen wants 8 electrons to be stable. So the solution to that is to actually share a second pair of electrons. Atoms can share more than one pair of electrons. So we might draw that like this. To show that they're sharing actually 2 pairs of electrons instead of just 1. And now when we count it all out, remember we're assuming those are shared, now we've got our 8. So 2, 4, 6, 8, 2, 4, 6, 8 for each. So that's what we call a Lewis dot structure. We can also just have a Lewis structure, or a molecular structure, where we replace those shared electrons with lines. So that would look like this. Now our counting and our, how we figure out if everything has enough electrons stays the same. We just know now that a line means 2 shared electrons. So when we count for this oxygen, we'd go 2, 4, 6, 8. And we count for this oxygen, 2, 4, 6, 8. All right, so that double shared electrons is sometimes called a double bond, a double covalent bond. Okay, and now we can look at nitrogen and kind of go the same way. I'm going to leave that one to you and see what you can come up with. And I want to jump over to an example of where this kind of stops working. And when I say stops working, I mean you can't really use the dots anymore, and we have to use a different method. So let's take a look at, we have one of those here. I guess actually for all of these, they will work with the dots. Well, let's look at CO. That's a good example. So let's start the same way. We want to know our valence electrons for each atom. So we've got C, which has 4, and we've got O, which has 6. Okay, so here's where we start to kind of run into a problem. We could kind of go about this the same way as we started with the 2 oxygens. So we could go, okay, we're going to share here because we know oxygen needs to share that one. We're going to share here because we know oxygen needs to share that one. And then we're going to write down that structure. That looks like this. So oxygen has 8 electrons now, 2, 4, 6, 8. But carbon still has 1, 2, 3, 4, 5, 6. So not 8, not an octet. So this doesn't work. But we can't share more electrons because then oxygen would have more than 8. So if we started like trying to do something like this, that would also be a problem because oxygen's going to have more than 8. So this whole dot method actually stops working for some of these compounds. So I want to show you a different method that's kind of the more standard method that will work for more and more compounds, even when the dots don't work anymore. So let's get rid of our dots. And here's the way that we do it beyond the dots. So to go beyond the dots, we need to first still figure out the number of valence electrons. And we're going to make a total of all the compounds. So we've got carbon and we've got oxygen. Carbon, we can look at the periodic table and see that it has 4 valence electrons. And oxygen, we can look at the periodic table and see that it has 6 valence electrons. And that means that we have a total number of 10 electrons to work with. So the difference in this method versus the dot method is we're going to distribute those 10 electrons wherever we need to put them. Because in a compound, the electrons don't necessarily have to stay with the atom that they came with. They can kind of get distributed around the molecule in different ways. So once we find the number of electrons, then we connect the atoms together. In this case, there's only one way to do that, CO, but we'll see some examples where there are some different possibilities. And then we distribute those electrons to try to fill all of those valences, to try to make 8 electrons on every atom that wants them. So we would say, okay, well, carbon has 2 electrons from this bond, so we'll go 4, 6, 8, and then we've got 2 left to get to 10, so we'll put those 2 over here. Now what you see, hopefully, is that that doesn't work, because while we've filled carbon's 8 electrons, we have not filled oxygen's. It only has 4. So that doesn't work. So we have to distribute these in a different way. And whenever you get in this situation where it seems like you just don't have enough electrons to finish or to fill everything out, that is that gives you a clue that what you really need is multiple shared pairs. If you don't have enough to go around, then there has to be more sharing. Makes sense, right? So what we can start doing is taking away electron pairs from whichever atom has more and sharing them instead. So instead of those 2 being only on carbon, we're going to share them between the 2. Now we're still not there because oxygen now has 2, 4, 6, but we're getting closer. So we can do it one more time, and then we'll have something that works. So now oxygen has 2, 4, 6, 8, and carbon also has 2, 4, 6, 8. And so that structure works, and we couldn't have really gotten to that structure just with the dots. We really had to pool all those valence electrons together and then kind of redistribute them however we wanted. And so that's a better way to do it that'll allow you to find structures for more atoms. Okay, before going on to another type, we're going to look at CO2, but I just want to pause there. Are there any questions or things that you don't quite get about doing this yet? Yeah, this is the preferred method for sure. The dot method, you never need the dot method. The dot method can be helpful because you can really see what the electrons are doing. You may encounter a homework question or a quiz question or something that says to draw the dot structure. But even if you do, you could always use this method and then put it back into dots. Just, take the lines and put them in dots instead. So the dots we kind of start with just so we can understand what's going on, but this is really the preferred method for most compounds, for all compounds really. Yeah. All right, let's look at CO2. So I want oh yeah, good question. So Daisy says, what if we have H and Be? So yes, it's true. There are atoms that don't quite fit these rules. And I don't know that we're going to see. Yeah, in this class, we are definitely going to see hydrogen. So hydrogen, as we already talked about, only gets 2 electrons instead of 8. There are a couple other exceptions also, like beryllium and boron, which can get less than an octet. And then there are elements down lower in the periodic table that can get more, can actually have more than 8 electrons around them. We're not really going to see that in this class. And all right, so what about when the 2 elements have 9 electrons together, work the same way? Well, so that actually becomes a problem, and that's one of the questions I think later on here, is you find this particular model, which is called the Lewis model, really doesn't work for odd numbers of electrons. It just fails. We need a better way of describing the structure for those. We have one. It's called molecular orbital theory. But drawing structures in this way doesn't really work for odd numbered electrons because odd numbers of total electrons. So which is actually kind of a good clue for you when you're doing these, if you come up with an odd number, chances are you added something wrong, unless it's a weird question that's like testing that in particular. I'm trying to see if there's one. So like, for example, let's look at NH4 plus ammonium ion. Nitrogen nitrogen has, yeah, I mean, you can do it with an odd number, but you're not going to fit it's not going to fit the rules because you can't have every atom having either 8 or 2 electrons if there's an odd number. So some atom, you can draw it, but some atom is not going to have an octet. It's not going to have 8 electrons. So like, take a look at this one. So if we do nitrogen and an NH4, that tells us we have a nitrogen and we have 4 hydrogens. So we want to add up our total valence electrons. So we can look at the periodic table, and there's nitrogen just above my head. That's in column 5, so that has 5 valence electrons. And then hydrogen we know has 1. So if we just were to add that up, you'd see it would be 9, right, which is an odd number. And we know that doesn't really work. And the reason that it doesn't work, well, we talked about why it doesn't work, but we're wrong here because we're forgetting about something. Anybody know what we're forgetting about? Why should this total actually be an even number and not an odd number? I mean, 5 plus 4 is 9. That is an odd number. Yeah, it's the positive charge that changes things. So positive charge means it's missing an electron, or it has 1 less electron. So we have to correct for that in our count. We have to subtract 1 electron. So our real total of electrons for this, valence electrons for this compound is 8. 5 plus 4, and then minus 1 because of the plus 1 charge. So then it becomes a little bit simpler. So this compound actually, yeah, hydrogen has 1 valence electron. So this one goes like this, right? And there's our compound, and that's actually the whole thing because that's 8 electrons, 2, 4, 6, 8. Nitrogen has 8, and each hydrogen has 2. And then because this is an ion, we put it in brackets and we put the charge up there. All right. Let's move over and look at CO2. So for CO2, we're going to start the same way. So we've got C, O, and there's 2 of them. So that's 4 electrons for carbon, 6 for oxygen, 6 for the other oxygen. So that's 16 total electrons. Now we're going to start building our structure, but we have a choice here. We can make this COO, or we can make this OCO. Which do we go with? Well, the correct answer is the bottom one. But hold on, let me answer a question here. Shouldn't each have 8? Or does it have 2 because they're 4? So hydrogen, because it's way up in that top row, hydrogen's valence shell only can contain 2 electrons max. So hydrogen's octet version of the octet rule, sometimes called the duet rule, is that hydrogen and helium only get 2 instead of 8. Does that make sense? So hydrogen only gets 2, not 8. Okay. All right, so over here, how do you determine the order, like how you set this thing up. So the answer for that is there are some various answers that you might find in books, but the most useful one I think for us is generally that first atom, whatever's listed first, is often the central atom, the one that goes in the middle. So usually these compounds are listed with the atom that goes in the middle first, and then the other ones that go around the outside after that. So that's a good rule of thumb. The exception to that is hydrogen. In acid compounds, hydrogen is listed first. But that kind of we can kind of figure that out because we know hydrogen only has 2 possible electrons. That's the most electrons it can have. So there's no way that hydrogen can ever be in the middle of anything because hydrogen can't like be surrounded by other stuff. It can't make that many bonds. Hydrogen can really only make 1 bond in the compounds that we're going to see. So when hydrogen is listed first, like in this compound here, it is not the central atom. It is going to be around the outside. But in all the other cases that you see here, so here's another example. Hydrogen would not be in the middle. Carbon would be in the middle, H on one side and N on the other. All these other examples, they're listed, they follow that rule. So PCl3, P in the middle, Cl is around the outside. NCl2, N in the middle, Cl is around the outside. SiF4, Si in the middle, F's around the outside. So this is our structure, and now all we need to do is fill in the electrons. Let me make clear that that's wrong, that that's not the structure. Okay, so then we've got 16 total electrons. We've already used 4, so that gives us 12 more. So I'm just going to start counting from 0, and we'll get up to 16 here. So 0, so we start with 0, we go 2, 4, and now we're going to start filling in octets. 6, 8, 10, 12, or sorry, 6, 8, 10. Now oxygen's done, it's got 8. We can move over to carbon. 12, 14. Now carbon's done, that's got 8. So we move over to this oxygen and we go 16. And what you notice here is that this one's not good. That doesn't work. This oxygen doesn't have 8 electrons. So that tells us that we don't have quite enough electrons for a fully singly bonded structure. We need to share some more electrons. And remember, with this method, we can take the electrons and move them around and share them however we want. So what I would do here actually, because it just to make it easier, is when you encounter that situation, especially as the molecule gets bigger and bigger, it's harder to kind of move things around step by step. So I might just start over and say, all right, that's not right. So I'm going to add a double bond here. I'm going to share an extra pair of electrons and redo it. So 2, 4, 6, 8, 10. So that's 8 electrons for that one. 12, that's 8 electrons. 14, 16. All right, so I got 8 electrons, 8 electrons. Oh, only 6. So we're not quite there yet. Now in this one, I can see that if I just take these 2 electrons and share them over here, I can make that work. If you don't see that, you can just take all the electrons off and start again with an extra pair of shared electrons and get something like that. And so that would be a correct structure. So now everything has 8 electrons, and we're all good. All right, so the question is, what if there are more than 2 elements? Well, so yeah, it gets tricky. It depends. Sometimes you can't necessarily get it to work. So here's an example where there's more than 2 elements, but we know one of them is hydrogen. So we're going to put the carbon in the middle with oxygen, and then we're going to have to figure out where to put those hydrogens, either on the carbon or the oxygen. I'll leave that to you, but it's actually some trial and error. So if you can get it to work, generally it's right. If everything has an octet and it works, it's right. Another clue when we get to multiple atoms, I want to see if there's some other ones over here too. Another clue is that symmetry is usually a good thing in these compounds. So if you can kind of distribute things more symmetrically, that's usually correct. But honestly, if it works, it's right. Yeah, so these will all be good. So if it works, it's right. If you can get it to work out where everything has 8 electrons or 2 for hydrogen, then it's a reasonable structure. And at least for me, I would still give you credit, even if it's not exactly identical to the true, actual, real structure, if you get it to work. Yeah, let's look at one. Let's look at this one down here. H3COH. So we're going to have to try some different things with this one because we're not quite sure how it's going to work yet. So first, we're going to start the same way we always do with adding up our electrons. So we've got 3 hydrogens, and each hydrogen is 1. Then we've got our carbon, which is 4 valence electrons, our oxygen, which is 6, and then another hydrogen over here, which is 1. And why isn't that hydrogen with all the other ones? Well, I don't know. We'll see. So we don't have any charges to worry about. So this means 6 plus 4 is 10, 11, and 3 is 14. So we've got 14 electrons to deal with, and we have to figure out some way to kind of put this thing together. All right, so we know that the hydrogen isn't going to be in the middle because hydrogen can essentially only make one bond. So we're going to put the carbon down first and connect it to the oxygen. And then we're going to try to figure out where all these hydrogens go. Now, looking at this structure, can you guess why the hydrogens are split up like this? Why this says H3 over on the left, and then there's this H over on the right? Why do you think the formula might be written that way? Well, any ideas? I don't know how far we are behind here, but it's kind of like an acid. Yeah, the hydrogens are written in this way to help you out. So sometimes structures are written in such a way that it kind of gives you a clue as to how they are connected. So what this is telling us is these 3 hydrogens are all on this carbon. And this one is over here on the oxygen. Now, if this formula were instead written H4CO to kind of put them all together, or CH4O, we could actually still figure this out because we know carbon can't have more than 8 electrons, so it can't make more than 4 bonds. So, and we know hydrogen can't make more than 1 bond because it can't have more than 2 electrons. So if we had something like this, and our first instinct was to go, oh, CH4, yeah, we'd realize like there's nowhere to put the oxygen now because we can't put it there because that doesn't work. And we can't put it there because now that carbon has too many. That's 10 total. So that kind of tells us, okay, well, that must not all go together. And in this case, this person wrote the structure so that it kind of helps you, or the formula so that it helps you out and it tells you, okay, here's how you're supposed to put this thing together. All right, so once we kind of have a structure like this, like the one that we have here, now we need to check our electrons. So far we've used 2, 4, 6, 8, 10 electrons. We've got 14 total, and this oxygen still needs some electrons because it's only got 4 so far. So that actually works out perfectly. We've got 4 more. Oxygen needs 4 more, so now we're good. Can we split the H, or does H3 have to be all on the same? You could split it up. Yeah, you could. There's a lot of trial and error involved here. So you may, when you see a formula, you kind of draw a thing out first, and it might not work. And if it doesn't work, that like you can't get all the electrons around properly, or if something has too many, if it doesn't seem like it's working, then that's your clue that what you drew was wrong and you should take it apart and try a different way. So yeah, so if we put all these three, I just put the three together because that's how it was written here, and I put them all on the carbon. But if that didn't work for some reason, like there was too many other stuff already connected there, then that would be our clue, like, oh, okay, I guess I have to take some of these hydrogens and put them somewhere else because it's not working. So there are really two things that you're looking for here when you do these structures. One is make sure every atom in the structure obeys that octet rule. So every atom has 8 electrons around it in the compound, except for hydrogen, which is going to have 2. And then secondly, look at your total number of electrons and make sure that it's equal to the actual number of valence electrons that those atoms bring in. And if it fits those two things, then it works, even if it's not maybe the absolute correct structure, because, you know, atoms are atoms and molecules are molecules, and sometimes they get weird. But the best you can do at this point is if you can fit everything in the octet rule and you have the right number of total electrons, then your structure should work. All right, so I think that's it for today. So try these out. There's plenty of practice left in here for ones that we didn't do. We're going to get into bond polarity next time. There's also, so on Mastering Chemistry this week, the first item in the assignment is practice using the tool to draw structures. So because you have to draw structures in Mastering Chemistry, it just kind of wants to get you used to that tool. And it's a little bit, it can be a problem. Like if you don't connect things just right, it tells you they're wrong. So if those kinds of things come up, just let me know. I can look at your answer and help you out with that. But you will be actually drawing these into the system when you do the Mastering Chemistry this week. And there should be plenty of practice for that. Please do the pre-lab quiz before lab. Yep, this is the testing for ions lab. So we're going to be practicing some naming compounds in that and also doing some tests. So make sure you read through the lab and then finish the pre-lab before you come into lab. And I hope it works this time. I don't know. I know we had problems with the pre-lab last week. So if anybody gets a chance to do it, if you could just send me a note and say it worked or something. Hopefully it does. If it doesn't work, let me know that too, and I'll either try to fix it or we'll just do like we did last time and just look at pictures and whatever. Yes, the next class is Thursday evening at 7. Oh, thank you. Alyssa says pre-lab works. Great. All right. Anything else? Okay. Well, thanks everybody. Let me know if you're having trouble on this stuff throughout the week, and I will see you Thursday night. Have a good day.